Hello everybody and welcome back. So we're going to be entering into the second part of the array class, and today we're going to be talking about the functions that actually generate arrays in Vex, so that the result of it is going to be an array, and then we're going to use what we learned in the last lesson to actually work with that array and figure out what we can how we can manipulate it or use that data for something useful. Okay. And then also just a few additional expressions that help us work with the arrays besides the everything we learned in the last lesson. Things like just reading a particular index, but actually ways of maybe sorting it or removing certain functions, adding two arrays together, those types of functions that we're going to need in order to correctly and efficiently work with these arrays. Okay, so let's get started. Now in my scene I've just got a basic grid and a wrangle where we're going to type a few functions and see how it works. And I've also just popped up my geometry spreadsheet at the bottom and the geometry at the top, just so we can kind of see what's happening in the scene and with the actual data. Okay, now I've got my help file open, and again I encourage you guys to use this, rely on it, particularly in the beginning, but actually in general you should be using this all the time. And I've got a few functions open that I want to show you. So the first function that I'm going to talk about that actually generates an array is the neighbors function. Now what you're going to see here, the type is integer array. Remember, the square brackets means it's an array, so this is saying that what it returns is an integer array. These are the exact type of functions we're talking about, ones that actually return an array, so then we need to know how to work with them. All right. So if we wanted to grab a particular neighbor, not just the whole list of neighbors, okay, well, there happens to actually be a function just called neighbor, right? So you can grab just one neighbor, but let's say we wanted to grab all the neighbors and then maybe iterate through each one, grabbing one at a time. You'd return an array, but then we'd use what we learned in the last lesson, where just at the end of our array, if we put square brackets and a 0, it's going to grab the first in the list of neighbors. Okay. So what this is going to do is return an array of point numbers of the neighbors of a point. And what neighbors means is, if I turn on my point numbers over here, just so we can see, neighbors means connected points. Okay, so the neighbor of point 34 over here would be 33, 24, 35, and 44. So they're actually connected by a primitive, and that makes them neighbors. This is not a proximity check. If you have just floating points, like in a point cloud, those points that are near to one another are not considered neighbors. Neighbors is only to do with connected geometry. Just now we're going to use a function that actually searches in space to find its nearby points. Okay, so it's very simple. We need to obviously store this in an integer array, so I'm going to say I array at foo, right? And I'm immediately just exporting so we can see it, because obviously we want to see the result, equals neighbors. And then we're just pointing at the geometry, so remember we can just use a 0 if we want to reference ourselves, and then the point number. So in this case I'm going to just use point number, because I want each point to grab its list of neighbors. Okay, and here's the result. So you'll see some points have more neighbors than others. The reason for this would be, look here at point number 0, you'll see that it, being in the corner, is only connected to point number 10 and point number 1, okay, by an actual polyline. Whereas point 11, if we find 11 over here, you'll see that it has 4 neighbors, because it's actually connected with 4 polylines. Right. So this one's pretty simple. And then let's move on to another one. So this series of expressions that I'm going to show you now are all kind of similar, and you'll need all of them depending on which way you're wanting to traverse your geometry. So there's point prims, which is a list of primitives attached to each point. There's prim points, which is the opposite, so it's the list of points attached to each primitive. there's also prim vertices, so that's the vertices for each primitive, and then point vertices, which is the vertices for each point. Okay, so sometimes you're going to have to figure out which one of these you need depending on what you're trying to do. Okay, so let's walk through a few of them and just see how it works. Right, so I'm going to type point prims here, which means we're grabbing all the primitives associated with each point. So we just need to feed its geometry. So I'm going to look at myself, so 0, and then a point number, right? And each point is going to tell you the primitive number of the primitives associated with it. So if I switch on my primitive numbers here as well, we're going to see what's happening. So let's take point 11 again, right? Point 11 is saying that it has 0, 1, 9, and 10. So 0, 1, 9, and 10. So these are not point numbers. These are the primitives that are attached to point 1. Point 11. Okay. And likewise, you'll see that something in the corner, so point 0 is only attached to primitive number 0. Okay. And then we can do the opposite function, which is prim points. So this will return the points attached to each primitive. Okay, so we'd feed it 0, and then we'd feed it the prim number. Okay. Now we can do that on point level, but then we're just going to get duplicates of the array. So I'll show you what I mean now. If I jump up to running over primitives instead, which is probably the most likely case where you'll use prim points, because you want all the points that are associated with the primitive. So you're probably going to store it on primitive level. So according to this, it's saying that primitive 0, so this one right here in the corner, has 4 points: 0, 1, 11, and 10. Okay. Now if we change this to point, it's going to store it on each point. And because we're running at primnum, each point knows what primitive it's attached to, and therefore all those 4 points, 0, 1, 10, and 11, are going to run the same function. So you'll see that they have the same value, 0, 1, 11, and 10. Okay, all of them have exactly the same. And you can use this to figure out, which points are actually attached to the same primitives. But most of the time, you're going to actually want to store it on primitive level. And then very similar to that is prim vertices and point vertices. So let's fill this in, right? So let's say prim vertices, and I'm gonna jump up to primitive level to store this. Okay. Now, what is happening over here? We're saying that we want the list of vertices that are associated with each primitive, and we're running over each of our primitives. So primitive 0 has the numbers 0, 1, 2, and 3. Now where are those? These points, these numbers right here, okay, see these blue ones are the point numbers and the red ones are the primitive numbers. Now we cannot actually see the vertex numbers, but you can display the vertex markers. And I want to just we're stepping a little bit away from Vex here, but there's some aspect of Houdini that I want to make very clear, because a lot of people struggle with this and don't actually understand what's happening, right? What are vertices versus points? Okay. Points have position. So if I also show my point markers over here, you'll see that blue dots are points. Points have position. I mean, we even call it point position, right? Which is P, V at P. But vertices do not have position data at all. You'll see under my vertices, all of these vertices do not have point position, okay? You don't put them in a particular place in space, but what they have is a primitive number and a point number that they are associated with. So for example, this first vertex is actually labeled 0, 0. In other words, it is the first vertex on primitive 0. Okay, so primitive 0 and point 0, and this over here would be our 0, 0 primitive number. Vertex number. Okay, and you'll see that they have an intrinsic data stored on it, which is the point number. So in other words, which point are they attached to? Okay, and you'll see that some of them have the same point number. Like for example here, 4, 1, and 5, 0 are both attached to point number 5. So let's go find that. Right, 5 is over here. Right, and we have 2 vertices attached to this one point. Okay. And it is 4, so in other words, primitive number 4, but vertex number 1 on that primitive. So vertex 0 would be there and 1 would be there. So that is referring to that vertex. And then 5, 0 is primitive 5, vertex number 0, which is attached to point number 5. Okay. Now this can be a little bit confusing, but just I hope that displaying it this way helps you see it. Vertices are essentially, you can almost think of them as the glue that connects primitives to points. Points have position, primitives do not have position either. But a primitive has a list of vertices. The vertices are connected to points, and the points have position. Okay, so you can imagine this primitive as like a big, canvas. It's almost like a tent, right? And the points themselves, the actual dots and these blue numbers are the pegs. Okay, they're actually pegged into specific positions in space, or pegged into the ground. Okay, the vertices are just the clips that connect the canvas to that point. And so you can have one peg at this point, like 11, which has 4 sheets of canvas attached to that one point. There are 4 clips, 4 sheets of canvas, but only one peg. And that's how this works. Okay. And I just want to make this clear because of the amount of times where a lot of my students are very confused about, they talk about like when you're modeling, you're pushing vertices around. You can't move vertices. Vertices have no position. Points have position. Okay. And primitives only exist when they have vertices in order to attach them to points. If we had to delete all the vertices from this primitive, then the primitive, although it would still exist, it would literally not display. Nothing would render, and it wouldn't display at all because it needs to be attached to points using vertices. Right? And you're going to see that later when we get to our final project, because we're going to be using Vex to generate geometry. And when we generate geometry, we're going to create a bunch of points. And when we want to connect them, we're going to have to create primitives. But the primitives are invisible until we create vertices to attach the primitives to the points. Okay, so I hope that makes sense, or at least a little bit more sense. We will cover it again later in a practical example to make sure that you are following. Okay. Right, so that's what we're doing here. We're just grabbing the list of prim vertices. Okay, so it's the vertices attached to that primitive, which will be 0, 1, and 2. If we go 0, 1, 2, and 3, so that will be those vertices attached to that primitive. Okay. Right. So let's move on. Just don't forget that there's also the point vertices. So if we want the list of vertices attached to each point, we can do that as well. Okay. Now, the next function we're going to be talking about is the PC find, okay, which is a point cloud find, right? This is performing a proximity check, okay? So this has nothing to do with connected geometry. All these other functions we've done up till now have to do with connected geometry. This is looking actually in space in all directions. You see here we've got a radius, so literally a spherical radius from a particular point, and it's looking for geometry. Okay, so be careful. This can be a slightly memory intensive function, so use it sparingly, or at least try to set the radius correctly so you're not searching your entire scene for one point. You should only really want to be searching a particular distance. Okay, so anyway, let's have a look at what we need to feed it in order for this to work. Okay, so first argument is the geometry. So in this case, let's just search on ourself. So I'm going to say 0. Then we need to feed it a P channel, so basically a position channel to read. Okay, now in this case, we're using geometry that's actually in our scene, but what you can do with this function, which is very powerful, is you can search for a basically proximity to a point based on something saved to disk. Okay, so a point cloud stored on disk, you can read it in and then check your proximity to that point. Okay, which is why we need to feed it a position channel. So this is just a string of the position channel, which is P in this case, right? And then we need to say, well, where do you want to search from? And we want to search from our own point position to see how close we are to the position in position channel. So we're going to say V at P. Okay. These are referring to two different positions. This is not the same thing. This is our own position, so each point's position, and then this is the position channel of the file that we're reading. Okay, but in this case, we're not reading a file. We're reading our own geometry, so we're reading from directly in the scene. Okay, and then we're going to feed it a radius. So let's pick something like 3. So we're going to search for 3 units away from each point, and then the maximum number of points that it'll allow us to find. So let's say 10 for now. And then close that and semicolon. Now let's have a look at what we've got. Right, so, oh wait, we're still on primitives. So let me go down to points again and have a look over here. So point number 0, I'm just going to switch off my primitive numbers and vertices again, but we'll keep the points, right? So point number 0 has found all of these points within this radius of itself. Okay, it has found point number 0, which is itself. Okay, now that's important to remember whenever you do a PC find. If you're searching on yourself, so your own geometry, if you use a 0 here, it is going to find itself, because obviously it is the closest point to itself, right? So if you don't want to include itself, you're going to have to run through all of these arrays and remove the first index. You'll see that each one of them, 0.5 has found 5 and a bunch of others. 0.8 has found 8 and a bunch of others. They will all find themselves. So sometimes you want that, other times you don't. And that's where we're going to use our other functions to work with arrays and actually remove that first index in order to check for our nearest points, but not including ourselves. Okay, so just keep that in mind. So it's found 0, it's found 1 and 10, it's found 11, it's found 20 and 2, and then it's found 12 and 21. Okay, but it hasn't found 22. So we can see that it has actually found everything in this kind of radius, but has not actually reached this point. And you'll also see that it has actually ordered it in the order of the distance. So you'll see it found 1 and 10 first, because they're quite close. And then it has found 11, because from here, like the radius would hit that first. Then as the radius increases, it'll find 20 and 2. And then it's going to find 21, okay, and 12. But then it doesn't quite hit 22. And if we increase this radius just slightly, we should find it hits, okay, well, let's increase it just a little bit more. It'll hit 22, but it won't hit 30. So, you know, you can see how this is working, okay? So we can perform a proximity check on ourselves, which can sometimes be pretty useful. But also keep in mind that we can perform a proximity check to other geometry. And this is not, you know, this geometry doesn't need to match in any way. All it's doing is searching for point numbers. So let's say we go to a polygon mesh here, but let me just reduce the number of actual points. I'll plug this into our second input, but then I'm just going to have to change our PC find value here, our geometry, to 1. So it's looking on this piece of geometry in its P channel compared to our own point position within a radius of 3 and a maximum of 10 points, which actually we wouldn't need a maximum of 10 points because there are only, oh wait, well, there are 17 points on here. So if we set this to 17, it would essentially find all of the relevant points if they fell within this radius. Okay, so what you'll see has happened now is some of these points have an empty array. Point 0, for example, has an empty array because we know that 3 units is only really making it in about this radius. Okay, but let's have a look at point 55. Right, so if we scroll down and find 55, so we'll see 55 is finding quite a few points, right? And these point numbers are not on this geometry, but on our sphere itself. Okay, so if I switch that on like this, so we can actually see the point numbers on the sphere, you'll see that 55, which is over here, is finding 11, which is the closest one to it, 7, which is the next closest, 16, which might be underneath here, there we go, 16, then it's finding 6, which is there, and so on. Okay, so it's finding most of the points available to it, and in fact it's probably limited. If we had to limit the max number of points, it's going to find the 5 closest points. If we increase that all the way to 17, it's going to find all the points that it can. Right. Okay, so that's how PCFind works, and PCFind is very, very valuable. Like I said, it can be a bit memory intensive, so be careful where you use it, but a lot of the time you're going to want to have points search on another piece of geometry. So for example, the attribute transfer node, if we drop down this attribute transfer, this copies attribute data based on position, and you'll see here that we have things like an actual maximum sample count, which is our maximum number of points, and then also a distance threshold, so this is a radius. So this is doing a very similar kind of function, and yet this node can actually be a lot heavier than doing a PCFind or a PCOpen, which we'll talk about later, to grab data with a proximity check. Okay, so I just want to show you that there's another function as well which is quite similar. So near points, which is very similar to a PCFind. You'll see that even the arguments are quite similar. There's geometry, but one thing it's missing is this P channel. And that's because near points is simply looking within your scene. You cannot feed it a path to geometry on file, and it is not reading a variable channel. It knows it's always looking for the P channel. Okay, so this is kind of like a shortcut version of PCFind if you want to go a little bit simpler and you know that you're specifically looking inside your scene. So we say near points, we give it 1 as well. We don't need to give it this position channel. We feed it our position, which is PT over here, and then it can take a max distance and doesn't need a max points. We can actually leave the max points out and it will find all of the points within that radius. But optionally we can include, so we'll run this different version which has all the same arguments except it also includes a max points, and then it will allow us to limit the points. And then we can run the same 2 functions here but just with an optional point group. So we feed it the string name of the group if we want to search only within a group. Okay. So then you'll see a very similar result over here, point 55, which is the one we checked just now. You'll see it will also be finding those same points, but it's going to find all of them within our radius of 3. If I reduce the radius, it'll obviously find less, but if I give it a massive radius, then it's going to be finding all of those points on the sphere, but ordering them based on the proximity. Okay, so even though this one, 55 and 54, are both finding all the points, they're listed based on which ones are the closest, okay, which can be quite useful to us. Okay, so those are the functions that we're doing to build arrays, okay, that are essentially returning arrays that we can then use. I mean, this, for example, this near points is returning a list of these points, and like I said, it's based on the order. Well, the order is telling us how close these points are. So if we wanted to check only the nearest 2 points, we'd be able to just work with this array, maybe drop the first index because we don't want to check ourselves, and then grab the second and third index and do something with it. Check the distance to them to see how far away we are from a piece of geometry, or whatever we want. Okay, so I'm going to now talk about functions in Vex, but these are not generating arrays. These are working with arrays, okay, giving us additional control over the array. All right, so I've got my Vex functions help card opened. Remember, you can find this just by typing Vex fun, okay? And right at the top, if we're sorting by like our tags, you'll see there's an arrays thing right at the top, okay? And you're going to use most of these to kind of work with arrays, but there's a few that are particularly useful and common, so I'm going to just run through them, right? Now the first one we're going to talk about is append. So I'm going to open up the card here, and I want to remind you guys what I mentioned when we discussed how to use the help file, that here we have a function that is void. What that means is that what it returns is void. It does not return anything. Okay, so this is not a function where we say, you know, whatever attribute or variable equals, and then we run the function in order to store the result of this in an attribute. If we had to store the result of this, we would get nothing, okay, because this is not giving us anything. Instead, it is acting upon something. And this ampersand, so the and sign, is telling us what it is acting upon. The other arguments that do not have an ampersand are values that we need, so arguments that help us know how to process this information, but they do not get altered in any way. They are used to alter this array. Okay. Now, I also mentioned before that there's a lot of correlation between string functions and arrays, because strings are treated very much like an array. It is an array of characters. Okay, so you'll often see when you use array functions that there's a string version and then there's an array version. And that's the same the other way around. Some of the string functions will actually work on arrays as well. So keep that in mind and be careful that we don't fill in the wrong one. Make sure that you look here for the actual array type. Okay? So here we're going to use this first one where we're appending to an array, we're appending a value. Now what append means is just it's adding the value at the end of the array. Okay, so we've got an array here with our near point, so I'm going to just leave this in as foo and we're going to test, right? So if I just say at foo, remember we don't have to put the typecast of integer array in because we've already typecasted once. So if I say at foo equals, okay, then I can change this, right? But I see I was about to make the same mistake that I was telling you guys not to do, which is that it's void. So we're not actually saying at foo equals. Instead, we're going to be processing the at foo value in here. So we just type append, open brackets, so you'll see that it doesn't say anything equals it, just append. Then we give it the array, and it is going to alter this array, and then we feed it a value. Okay, so let's just say 10, and then close bracket. Okay, and you'll see what it's done here is added to every one of these arrays has the value 10 appended to the end of it. Okay, even the ones that were empty. Okay, so that's what append does. And what you'll also find is that there is another function called push, and push does exactly the same. Even here it says it's the same as push, right? I believe it's just from sort of other coding languages. Some of them call it append, some of them call it push. So it's a sort of a way of making it easier for us that they've created an alias for this function. But because push is appending values, we might as well just use append. I tend to use append, but if you are used to using the word push, then go for it. It does the exact same thing. Also, you'll find that there's another method of this, which is we're appending an array of values to an array. And all that means is, we're just joining the two arrays. So if we have another array, so let's say I just create I array at test equals, and then we just give it a few values, maybe 1, 2, 3. Okay, so we're creating a test array, and then instead of appending just one value, we actually feed it another array. Then it will append that whole array 1, 2, 3 at the end. Okay, so this is a way of joining two arrays if you wish. All right. So append, very, very powerful. Then let's talk about insert, because sometimes we want to not add to the end of the array. We actually want certain values inserted in the middle of the array. Okay, so now here we have another void function. So we're just going to be running the insert function. So I'll clear this, and I'm going to say insert. Okay, and again we have a string version, but then we have two array versions, one where it's a single value and one with another array. So let's start with the first one. We're going to act upon our foo array, right? And then we're choosing which index to insert these values into. Okay, so if I say 5, and then I give it a value of 10 again. Okay, and let's have a look at what's happened here. And something very interesting has happened. Okay, so if we look at maybe some of these longer ones, you'll see that it has inserted the value 10 at the 5th index. Okay, so 0, 1, 2, 3, 4, 5. There's a 10, and there's a 10 in all of them at that particular index. But also note what has happened to the arrays that were previously empty, or the arrays that were not empty but had only one value. If I just comment this out, we'll just show you that some of them had, like here, 8, 3, 13, but it doesn't have a 4th and 5th index. And yet when I have this, you'll see that it has actually inserted zeros and then created our 10 at index 5. Okay, so this may or may not be the result you want. Just be careful. Okay, that's why append is quite useful, because append is going to insert it at the end and will not create a bunch of null values that you don't want. Okay, but in other stages, like in other circumstances, you might find that this is exactly what you want. It doesn't matter the size of the array already. You want to make sure that your 5th index is 10. Okay, or instead of feeding it a single value, we can feed it a list of values. Okay, so then at the 5th index, it will insert the first index of the second array, and will insert the rest after that. Okay, and push up all the other values till afterwards. Right, so you'll see even in this long one, at the 5th index, we've got 1, 2, 3, and then we go back to the rest of our values. Okay, so that's how insert works. Then let's talk about pop. So pop is essentially removing a particular index from an array, and it returns that array. So this is doing two things. Very, very important to note this. This is not void, so it returns a particular value. And the reason it says type in these triangular brackets is because the type of the array will determine the type that gets returned. So it could be a string, it could be an integer, a float, or whatever. Okay, so it is going to return the the value that we pop out of this array, but it is also going to act upon the array. So there is an ampersand sign, which means it is going to change this array. Okay, this is very different to if we just wanted to find out, if we just wanted to return the value of a particular index in an array, but without changing the array. Then we would use what we spoke about in the last lesson. Okay, so let me show you this as an example. If I say I at I don't know, test2, okay, because we're already using test, so I'm just calling it test2, okay, equals, and then I say pop at foo, so we feed it the array, and close. That's all. We're just going to do this first version where we just feed it an array. What this is going to do, it's going to pop the last element of an array, kind of the opposite of an append. It's going to take the index at the end and return it, as well as changing the array itself. Okay, so you'll see here, before we do it, that this on point number 11 has 9, 4, and 14. Now when I activate this, it goes to 9 and 4. So it has actually removed 14 and then returned it and stored it in our test2. Okay, if this is what we want, which sometimes it is, then great. If this is not what we want, and we want to leave our array untouched, but we just want to find out what the last value is, then instead of popping, we would just run @foo and then grab an index. And remember that -1 will grab our last index. So you'll see that when I hit insert there, test2 is exactly the same. It's still equal to 14, but our original array is left untouched. Okay, two different methods, two very different results, and it depends what you want to do. Now if we go back to our pop version, okay, so pop, and then we feed it @foo, but we actually give it an index. So instead of actually wanting to pop the last index, we rather want to pop index number 5. Okay, then the result will change. Now obviously we're getting a 0 returned when we don't have any index at that, any values at that index. For example, in any of these that are empty or the ones that are just too short. But then over here, you'll find that it removed. So let's go back. We want to look at number 5. So 0, 1, 2, 3, 4, 5. This is 13. It's going to take 13 out. It's going to set test2 to equal to 13. And then it will remove it from here. So let's remove that. And there we go. 13 has been removed and inserted there. Okay. So that's the difference between pop and just referencing a particular index. Okay. And in line with that, I want to talk about remove index, which is very much like, it's exactly the same as pop, which we just spoke about. In the same way that append and push are similar, in this way pop and remove index are similar as well. You know, in fact, append is very much the explanation of what it's doing. Push is the kind of the old school, almost nickname for what that function is doing. Well, in this case, pop is actually that nickname, and remove index is the more descriptive one. So you guys are welcome to use whichever one you want. Okay, so it's just going to remove a particular item from a given index from an array. Okay, but there's another very powerful, very cool function over here called remove value. Okay, so remove index is going to do exactly what we just did, popping an index. Okay, so we tell it which position in the array to grab that value from, and it's going to return that. But remove value is going to find, it's going to search through the array and find a value, and then it's going to return the a 1 if it actually was able to remove it, or 0 if not. So in this case, it is acting upon the array, but it is returning something, and what it's returning is kind of just like a test to say whether it found a value in there or not. Okay, and just please note that it is returning, well, it's going to remove the first instance of the value that it finds, only the first one. Okay, so if you want this to remove all of those values, you will have to iterate through that function, and we can actually build something like that later on in the more advanced classes. Okay, so let's try this. Okay, so let's just keep this open so we know what we're doing. So it's called remove value. So let's say here we're going to say I at test2 equals remove value, and then we feed it the array that we're going to act upon, so foo, and then the value that we want to search for. So let's say 1, right? Now what you're going to see over here is some of these under test2 have 0. This means that it failed to remove anything. Okay, so it did not find the value 1 in any of those arrays, but this one, it found a value. Okay, so if I disable this, we'll see that there was a 1, and now when I re-enable it, that 1 has been removed, So the original array has actually been changed, which is what that ampersand sign tells us. And then test2 is saying 1. In other words, yes, I have found a 1 and I removed it. Okay. If I say 5 instead, then only the ones that found a 5 will say 1. Yes, I removed a 5. Okay, but then these all that say 0 are saying nope, I found no 5s in the array. Okay. Right, let's move on. So, very simple function that we're going to use very often, len, which is just giving you the length of the array. In other words, how many items are there in that array. Okay, so I'm just going to keep I at test2, but I'm just going to say len, and I'm going to point at our array. Very simply, it's just going to tell us there are 3 in here, which, see, 1, 2, 3. There are 11 in here, there are 17 in there, there are 15 in there. Okay. So that's all it's doing. It's just counting the number of indices that we have, right? You can also grab the length of the string and of a matrix and of a vector. So very powerful function. Okay. We can also resize. So resizing an array, which you'll often need to do, is another void function. So it's just simply acting upon the array, and we're telling it what size we want it to be. And by size, I mean kind of the opposite of this len. Okay, so we're going to clear this, and I'm going to say resize at foo, okay, which is the first argument we need to feed it. And then the second is how big do we want that? So we say, let's say 10. It's going to make sure that all of the arrays are exactly 10 in length. The empty ones are now just filled with zeros. The ones that were short are still filled with zeros appended at the end, and the ones that were longer are trimmed to exactly 10. Okay, so sometimes you'll need to resize an array with 0 values, and then you loop through this array, filling each value. Okay, so there's quite a few scenarios where we're going to actually need to use a resize. Okay, and then argument sort, okay, arg sort. Okay, so sometimes you'll see, like I said before, the order of an array is actually important. Okay, in this particular case, because we're using near points, the order is telling us which which points are the closest, right? They're ordered in terms of proximity. But what if we don't want that? We want to grab all our nearest points, but we actually want to loop through them in terms of point order. Right? Well, we can do that. We first grab the array just by running near points, but now we can arg sort. Okay, so let's pop this up and have a look. Okay, it's going to be returning an integer array. Okay, so it's going to be returning another array, but the array that it is returning is not the altered version of our array. Instead, it's a sorted sequence. Okay. So it'll be easier to show you this when you actually see it. So I'm going to say I array at test2. So I'm going to be creating a new array, and I'm going to say arg sort, and I point at foo. Okay. So let's have a look at what this has given us. All right. So let's take point 11 here because there's only 3 values, so it's easier to see. Right? It's taken this array that we fed it. It's sorted it in terms of order. So 4 is less than 9 and 14. Then it's 9, then it's 14. So it's essentially put this in numeric order. Okay? But it hasn't altered the original array. Instead, it has returned an array of the order of those index. In other words, the order that the indices should be. So what it means by 1 here is it's saying if you have to go to this array, take the first index, well, the second index, which is index number 1, which is 4, and it's saying that one should be first. Then index 0, which is 9, and then index 2. Okay, so over here you'll see, take on maybe a longer example, it's saying that index 10 should be first. So we look here and it's index 10, if we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 0. And obviously in this order, 0 is the smallest number. So it's saying that is the one that should go first, then 9, then 8, then 2, then 4. Okay. Now, We can use this for multiple things. One thing we can particularly use it for is another function which is called reorder. Okay, so essentially this is applying that new array, this sequence list, to our original array, and what it's going to do is return the new array. So it does not have that ampersand sign, so it's not acting upon our original array. It's returning a new one. So if we want to override the old one, we would have to say over here, we would have to say at foo equals in order to actually reorder foo without creating a new array. Right? I hope you guys are following with that. So we're going to say reorder, and then let's see what arguments we need. We need to feed it the values that we want to reorder, and then we're going to feed it the list of indices in that correct order. So essentially we're feeding it foo, and then we're feeding it test2. Okay, and you'll see here all of these have stayed exactly the same length, same values are in here, but they've all been reordered in terms of ascending order numerically. Okay. There is also, if we do want to, there is a reverse function, okay, which just returns that array in a particular, well, in a reverse order. So instead of feeding it this array here, we could maybe inside of this, we just return a reverse. So we could reverse the index order, which would reverse it here, or we could instead reverse the entire result. Either way, it's going to result in the same thing. Okay, so now it's in descending order numerically. Okay, now I'd just like to point out that there is a quicker, simpler way to sort an array if we just want it in ascending or descending order. Okay, so if we go under argsort, you'll see it even suggests it to us over here, which is just called sort. Okay, let me just expand this so we can see. So this is just going to return an array that is sorted in increasing order, and then we could use a reverse if we want to. Okay, so we could go, and then let me just say I integer array at, I'm just going to create foo2 just so we can see, and I will just say sort at foo. Okay, so foo2 will be sorted in increasing order. So this is a lot faster and a lot less steps. And if this is actually what we want, then sure, you should use sort. It's just a lot quicker. Or like I said, yeah, you could reverse this if you wanted it in the other order. But the reason why this whole method exists of creating an index sort of sorting order and then being able to reorder something based on that index order is if we wanted to insert other functions in between. So you wanted to manually go and force your sort order in a particular way, or if what you're trying to sort is by a different kind of argument. Okay, they give a really good example of this in under argsort, right, in here, where they say you've got an array of strings. So you've actually got the word red, green, blue, orange, violet, and indigo. Okay. Now, these have no order. I mean, you could sort them alphabetically, I guess, but if you wanted to sort these by the length of their names, so in other words, red having only 3 letters should be first, then blue would have 4 letters, so blue would go next, and so on, and you'd sort of count the number of letters in each word and sort your array by that. Now, in order to do that, you'd have to do an argsort, and you'd argsort using a new array. You'd create an array of the lengths of the names. Okay, so you'd run a len function, which we just learned about. And like I said, you can run a len on strings as well as arrays. So the len function for red is going to return 3. Okay, and you're going to append that to this lengths array, and then create essentially the sorting order that comes out of argsort. And then you're going to use the reorder function that we just learned about. You're going to reorder your color array, but you're reordering it using this new order that you created, which was based on the lengths of the name, not just, alphanumeric sorting. Okay, and the result would then be red, blue, green, orange, violet, indigo in order of the lengths of their names. Okay, and you'll also find that in this particular case, something that is worth noting is that when things have the same number of letters, then, you know, or whatever other argument you're sorting by, if there are things with the same, then they will be left in the original order. So orange, violet, and indigo stay in that particular order because they have the same number of letters. Okay, so they're going to stay exactly that. But these will be reordered because they have actually, you know, fewer letters, and so 3, 4, and then 5 letters. Okay, right. So that about wraps it up. There's just one more really cool function that I want to show you, but it's not actually listed here in arrays, and that is find. Okay, find is actually under string functions. Okay, but like I said, you know, whenever there's strings, you can probably apply the same function to arrays. So here's the string version, but you see, you scroll down a little bit and you'll find there's an array version as well. So we can just search an array for a particular value. All right, so let's say I say what it's going to return is an integer, and that integer is going to, I believe, will be the index of where it has come from. So we say I at test2 equals, then we run our find function, we feed it our array, and then we feed it a target. So let's say 1. Okay, so we're searching for the number 1 inside of this. Okay, and what will happen is on any arrays where it has found that function, it will return, that value, it will return the actual index number of where it found it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. See, at 9, in the 9th index, right, it's found a number 1, and it will return that. The ones where it fails to find a 1, it does something quite odd, but it's actually quite cool. It returns a negative value, which is equal to negative the length of the array minus 1. Okay, and the reason for that, I mean, if you just wanted to check whether it succeeded or failed, you could just check whether it's greater than or less than 0. Okay, but it also returns it that way so that it will cause an error, right? It even explains it in over here, right? That it's minus the length of that value minus another 1, okay? Because it's intended to cause an error if you try to use that value as an index when grabbing from the array. Okay, so very, very cool functions. I hope this will help you guys. This is the majority of what you'll need in order to work with and manipulate arrays, and also now you know a few functions that are actually generating arrays. So if you ever see one, you know, you need to search for all of your neighbors, you know exactly how to work with them. You can create a list of neighbors, or maybe PC find, you know, so your nearby points, and then you can loop through them. You can grab the furthest point within that array, or the closest point, or maybe the exact middle. You can use arrays to calculate other averages. So besides the mean, which is your normal average, but you can also calculate your mode and your median. So arrays are very, very, very powerful. And also when we do loops, in the next lesson, we're going to be talking about blocks and loops. You're going to want to be looping over arrays as well. Okay, so I hope that all made sense and that it wasn't a bit too much. Please, there's a lot of resources out there for what arrays can do and what you can do with them. So if you are confused, please do some more research. Okay, and I'll see you guys in the next lesson.